Hello again, everybody. This is the second video. I'm hoping that these are going to be helpful to you throughout the year. Today I want to talk about the types of motion, and the setup for this was the classroom activity that we all did, where we walked around the classroom and you took notes on different types of physics toys that we had. And I want to give some sort of credence to what you saw by giving you the official physics definitions that describe the motion of the toys that you saw. So the first definition I'd like to give you today is constant motion. And constant motion happens whenever you have an object that is not what we call accelerating. And we'll get to what that is in a second. But the acceleration of that object is zero. The object must either be moving in a straight line in one direction at a constant speed or at rest, meaning it's not moving, it's not doing anything. So when you have an object that's accelerating, we actually like to say that it is changing either velocity or it's changing direction. And you will see, this is direction, and you'll see this little triangle. It's actually the Greek letter delta. And as you sit in math class, you will see delta more and more. It just means change in a mathematical sense. So we're having an object that's either changing velocity or direction. Now velocity is actually sort of its own little enigma. Velocity for you probably just means speed. And in physics land, that's part of the definition. Velocity is speed, but in order for it to have velocity, it is speed in a certain direction. I hope that as the year goes on, my writing on this tab will get better. But for now, it is what it is. So when you're accelerating, you're changing speed or in a certain direction, or you're changing direction. All right, so velocity is speed in a certain direction. We'll get into the difference between that and regular speed in a couple of days. But for our purposes, an acceleration, or for something that's going through constant motion, it's not accelerating. So you can either change velocity by speeding up or slowing down, or you can be changing direction. So for something that is undergoing constant motion, it's essentially an object, maybe, I don't know, a car. Yeah, it's a car. Just go with it. That is going at a constant speed, just kind of ticking, tick, 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 at a constant speed in a constant direction. So that's what constant motion is. Continuing, we have something called accelerated motion, where is the opposite of the constant motion. You have an object that's accelerating if its velocity is changing. And I can't stand the fact that it is grammatically incorrect here. If its velocity is changing, an object apostrophe S, velocity can change in one of three ways. It's either speeding up, slowing down, or changing direction. So there are three ways to change an object's velocity. There are three ways to accelerate an object. You can speed it up, slow it down, or change its direction. So unless you have an object that's going straight across, if you've got a curve, if you've got something that's speeding up or slowing down, it is changing its velocity. So these, a curve or a change in speed, are accelerated motion. This is constant motion. All right, so it's a very big distinction. And when we get into some equations, you're going to use some equations to deal with accelerated motion, and you're going to use different equations to deal with constant motion. So it's a very big distinction that you have to draw. You have to get really good at noticing if something's velocity is changing or not. The third example of motion that we saw was something called simple harmonic motion. And there are three components of simple harmonic motion. First off, the motion repeats indefinitely. Think of something that is just going to keep doing its motion and never stopping under quote-unquote ideal circumstances. In the absence of friction, in the absence of air resistance. And these are all things that we're going to learn a lot more about, but I'm hoping you know that friction kind of drags stuff and slows stuff down. And I'm hoping that you know air resistance slows stuff down. But under ideal circumstances, you are never going to have simple harmonic motion stop. The second component is the motion is cyclical, meaning there's a pattern, a cycle of the motion that gets repeated, such as moving back and forth or up and down. So two examples that you should probably be paying attention to are the pendulum, where you've got the ball there and it and then it becomes the ball over here and then it goes back and then it goes this way and then that way and then this way and then that way, and it just never ever stops. It does slow down, but that's because there's friction from the air that slows it down. If there was no air resistance, this pattern would go forever. And if you've ever been to the Museum of Science, there is that huge, I don't know, glass cylinder at the Museum of Science. And in the middle of the glass cylinder, there is a string with a little pendulum, and it just swings back and forth and back and forth and back and forth. So, you know, that's an example that I hope you know where you've actually seen a pendulum before. The third and final stipulation is that there is, in fact, what we call a restoring force. The object can only repeat this if there is a singular force that keeps it returning. So a lot of people actually mess up and they think that the bouncing ball, specifically the happy ball that bounces, hits the table, and bounces back up, is simple harmonic motion. You got to realize that the restoring force here is different than the restoring force in, say, a pendulum. So with the bouncing ball, you've got gravity pulling the ball down, and then you have a collision. You have elastic force. You've got the ball getting squished on the surface of the table, and that squish is what makes it restore back up. With the pendulum, you've only got gravity, which pulls the ball down, and it wants to go down, and the ball gets going, and then as it comes back up, gravity's still pulling the ball down, and it goes back this way, and it comes up, and gravity's still pulling the ball down, and it goes back this way. So essentially, when you're dealing with a true simple harmonic motion, specifically in the idea of a pendulum, you're only dealing with one force, and that force is gravity, and that is a restorative force. Here, you've got a few different forces acting, and they're actually acting on different objects here. You've got gravity pulling the ball down. You've got a collision that acts between the ball and the table. Another example of simple harmonic motion that you saw was, and you're going to need to forgive me, this is a spring with a mass on it. And if you remember, the mass would drop, and there would be gravity pulling down, and then the mass would go up, and that was because of a force caused by a spring. So you've only got two forces, and gravity is always trying to restore the mass going down, and the spring force is always trying to pull the mass going up. So you've got really two forces, and they're both acting just on the spring. Here, and we'll talk about this later on in the year, the ball is getting acted on by a table, and the ball is acting on a table. In both of these, both forces are acting on the spring. So there's no third weird random object involved. Fair enough? So simple harmonic motion, three components. I would know all three of them, and I'd be able to recognize that there were two at least, unless you can think of another one, simple harmonic motion demonstrations during the walk around activity that we did. Next is linear motion, and this is really, really tough to understand. It's an object that goes in a line. That's it. Tough, huh? So the object moves in a linear path, a straight line. It doesn't have to be the same direction. It does not have to be the same speed. It does have to be the same direction. Well, actually, I'm going to leave that. Because you can have an object doing linear motion if it goes this away, and then it goes that away, and then it goes this away, and then it goes back that away. So that's linear. So the direction that we're dealing with, it would be the same axis, being x or y. All right. If you've got an object going, a ball, and it's going a little curvy, that is not at all linear. Okay. But it can be moving back and forth, but it always needs to be in a straight line. Then you've got this thing called circular motion, and I'm not even going to try and draw a circle because I supposedly have ways in here of drawing circles and such. There we go, shapes. So let us draw a circle. Beautiful. And now we can do some good stuff to the circle. But regardless, the object is always going in a circular pattern. The object's positions change constantly in such a way that the path drawn out would move in a circle. You saw a few of those. Anything attached to a rope, giving it a set radius, is an example of a circular motion. So there's my R. Okay. Next, rotational motion. The object actually spins on an axis, does not have to change position to rotate. So this is something that, sort of just like a top, is making its own rotation, but it is not necessarily moving in that circular path. So I remember in a few of the classes I made sort of a big deal of where one of the objects was actually placed. You know, if it's placed in the middle of something, it's spinning, it's rotating. Whereas if we move it to the outside, the object itself is making this progression all the way around a circle. So it's a very big distinction to make. And, asterisk, an object can both spin and rotate. One example of this is the Earth going around the sun, which produces the seasons, and its rotation about the poles, which gives us day and night. So you've got the Earth, which is doing this daily thing. Oh boy, that's not what I wanted to do at all. You've got the Earth, which is going around the sun. I'm just trying to get rid of that. At the same time, it's also spinning. It's also rotating. So you've got this precession around the sun, and then you've got this spinning around the axis. So here in the middle, let's make the sun. I can make my pen up here. There's the sun. Here's the Earth. That's my circle. And the Earth is both going in circular motion, but at the same time, here's the Earth. It's also spinning around its north and south poles. So you've got a very distinctive thing where you've got both ideas happening at the same time. It's very important that you be able to differentiate between the two, because there's one set of rules of physics for this, and then there's another set of rules of physics for that. This being circular and that being rotational motion. Finally, you've got some what we call projectile motion. And projectile motion is also known as free fall. It happens when the only force acting on the motion of the object is gravity. Anytime you shoot something or throw something or launch something, it is projectile motion once the object leaves your hand, or once, if it's a rocket, once the fuel runs out. You're essentially dealing with a ball that you've thrown up, and the ball is going up, and gravity is the only thing acting on it, pulling it back down. You got gravity pulling it back down. One-dimensional projectile motion is when you have an object that is going up or down. Only up or down. So this is one-dimensional projectile. And it's accelerated because gravity is actually causing the ball to slow down as it's going up and speed up as it's coming down. So you've got a couple of things going on here. Remember, acceleration is a change in velocity, a change in speed. So going up, it's slowing down. Coming down, it's speeding up. And in the middle here, you have a change in direction. So it actually satisfies all three criteria for being a change in velocity or an accelerated motion. Two-dimensional projectile motion, and this is a big deal. You've got one-dimensional projectile motion and two-dimensional projectile motion. Two-dimensional projectile motion happens if you've got a movement in two dimensions. So you're now shooting at an object that sort of, if you're throwing a ball or if you're launching into a pirouette, where you leave the ground going one way, and you've got both what we call a y component as well as an x component to your motion. Whereas one-dimensional projectile motion, you only have what we call a y component, and that's why when you're sitting in algebra class and they're making you do a graph, and you've got the x-axis and the y-axis. The y, we always talk in physics about the vertical axis, and the x being the horizontal axis. If I can spell. So, in two-dimensional projectile motion, you're dealing with both the y, the vertical axis, and the x, the horizontal axis. Whereas one-dimensional, you're only dealing with the y vertical axis, no x. So that is essentially everything that you can break down all the motion that we saw the other day in those key physics phrases. And what I'd like you to do, and I told you I'd explain this to you during this video, now that you've got some definitions for yourselves, I'd love to see you make a little chart. And it should look something like this. I'm not going to, you can do it in an Excel spreadsheet, you can do it in Google, you can do it in your notebook with a pen, but just to kind of set it up, and I'm not going to do the whole thing, but you guys should definitely feel free to do the whole thing. We've got the stations, the pendulum, the happy sad ball, happy, sad, and all the other stations. If I remember correctly, there were 9 stations. Up here, you should definitely be putting down the different types of motion that we're dealing with. So if you were looking at accelerated motion, A, C, C. If you were looking at constant motion, you're looking at projectile motion. If you're looking at circular, if you're looking at rotational motion, these are all, your chart can look something like this, and it would be perfectly awesome to do that. So, and finish out, there's obviously a few more words up here that, now that my computer is being angry with me, I don't want to draw, but accelerated motion, constant motion, projectile, you can figure out the rest of it. And all you really should do is just, the happy balls, they seem to be accelerating. They definitely were not constant motion because we dropped them. They were speeding up. They were projectiles, and just check off. And all we'll do on Tuesday or on Monday is come back together and compare and contrast our charts. So that's what I'm hoping to see. If you watch this video, you'll have this chart. I hope that this video was helpful. And if you have any questions, please feel free to shoot me an email. Other than that, I will see you all on Monday.